The focus of today's session is to develop an understanding of operating systems. You should be able to explain why a computer system requires an operating system. You should be able to explain the key management tasks which are carried out by the operating system. And chances are that some of these are going to be very familiar because a lot of us actually use operating systems on a daily basis. You should then show understanding of the need for typical utility software provided with an operating system, things like disk defragmentation, virus scanners, and so forth, and then show an understanding of program libraries, including DLLs, which stand for dynamically linked libraries, and we'll be talking about that today as well. So let's begin by delving into the history of operating systems and how the need for operating systems developed over time. Now, as usual, there are quite a lot of key terms and you need to be familiar with these, so do pause the video and jot these key terms down. These are basic definitions that we'll refer to throughout the lesson and beyond. So start by looking at CMOS, which is complementary metal oxide semiconductor. These are little tiny semiconductor chips which are used in hardware and CPUs. Operating system, obviously the definition of what that is. HCI, human computer interface, how a human interacts with a computer. GUI, graphical user interface, the use of icons, menus, and images. Command line interface, basic command prompts, text. Commands are entered here, very old style, but you can still encounter them these days. Icons, small pictures or symbols. WIMPs, interfaces, a Windows icon menu and pointing device interface. Basically every desktop operating system uses it. And then we move on to memory management, optimization, organization. Now these are part of the operating system that controls the main memory. They ensure that it functions to the very best efficient standards, and it determines how much memory is allocated to different applications. Security management is that part of the operating system that ensures integrity, confidentiality, and availability of data. Virtual memory systems are again to do with memory management, especially when you run out of RAM. How would you compensate for shortage of actual physical memory? And we'll be looking at that in due course. And then you've got memory protection, which is a function of memory management that ensures that if you have two competing applications, they can't use the same memory locations at the same time because that could lead to crashes. Do pause the video and jot these down before we move on to the next set of definitions and key terms. Okay, same rule as before. Pause the video, jot these ones down. A bit technical terms now. You probably haven't encountered some of these before. So process management is part of the operating system that involves allocation of resources. It permits the sharing and exchange of data. Hardware management is something that you can probably guess. It allows all input-output devices connected to a computer to make use of the CPU, so it gives that control. And of course, to allow that control to happen, device drivers, which are basically software that communicates with the operating system, and the hardware, those need to be installed. You got utility programs, which are part of the operating systems, but they carry specific functions like virus checking, disk defragmentation, and so forth. You've got disk formatters, which format disks to make sure that data can be stored and retrieved. Then you've got bad sectors, which are faulty sectors on hard disk drives, which can be soft or hard. And a hard one is obviously physical damage. Soft one could be software based. And then you've got antivirus software, which is pretty straightforward. Heuristic checking is a technique that antivirus software uses to check the behavior of a possible file to indicate that it's like a virus, because sometimes you can't actually detect the viruses because the definitions are so new or they haven't even been discovered yet. So when a file starts behaving like a virus, it can just take a guess. So heuristic is decision making basically. And then you've got quarantine, which basically a virus scanner will quarantine a file to ensure that it can be dealt with. The next set of terms that you see on screen again go into the nitty-gritty of the various different utility software. So false positives can rise as a result of heuristic checking, and disk defragmentation, content analysis software, compression, backup utilities. All of these are utility programs that are built in the operating system to do one particular task. So do pause the video and jot these down. And finally, you've got program libraries and library programs, library routines, dynamically linked files, DLLs. All of these are preset pieces of code which can be freely accessed by other software developers, and they are used to extend programs and give greater functionality within the operating system. So again, pause the video and jot all of these down. Okay, so we'll begin the lesson with an extract from The Hitchhiker's Guide to the Galaxy, one of the best books ever written about science fiction. And I like this particular extract, which kind of highlights the need for operating systems and how you could actually create functionality without having the need for an operating system, but it can be quite intricate and quite tricky. And at most times, it's very, very basic. So starting with basic, let's start thinking about what your own prior knowledge is about this particular topic. So think about, what operating systems do you use? What does each operating system allow you to do? So think about the one that you're using perhaps with your mobile phone versus the one that you have for your desktop. Or you might want to compare it to the one that your smart TV might have. How would or could you perform the tasks that you currently do with an operating system on a computer without one? How would that function? How would the audio video work out? How would you be able to display in different resolutions? All sorts of things can come into play here. So think about those things, and it's just to kind of get your mind going about how sometimes operating systems become secondary. We use them, but we never think about them. Especially think about your microwave. It might have some instructions built in, which might be very, very basic, but we use them all the time, but we never think about those. And we often think that they probably are hard coded into BIOS, as was the case with early computers, because early computers had no operating systems. Control software often was loaded each time using things like punched cards, and this was very slow and cumbersome. And then later, as we know, ROM and hard disk drives allowed us to have operating systems installed to make the entire user experience much more efficient. Imagine every single time you want to use your microwave, you've got to load some punch card in just to kind of get the computer to understand what it should be doing. That would be so annoying, because right now we just find it inconvenient to just press a few buttons to turn it on and have the right settings. Most people even don't use microwaves efficiently because they just have a preset temperature and they just type the time in or press the button for the time, and there they go. Now imagine actually having to put code in every single time you want to use it. It will be very terrible. People won't use it. But the operating system, and how did it all develop? The story goes back to the artist who gave the Mac a smile. And what I mean by that is that icon that you see on screen is an early example of how we used images to represent commands. Before this, everything used to be text. That was the next part. So instead of punch cards, we had to type commands in. And that also was very tricky for the non-experts, because you had to remember so many different types of commands and think about maths and the kind of technical language it uses. It switches a lot of people off. It becomes the domain of experts, and that's exactly what was happening with computers. So along comes Susan Carey. She's one of the greatest female graphic designers, and she's a pioneer of graphic design for digital interfaces. And since 1983, she's designed thousands and thousands of icons for leading companies all across the world. And you'll probably see some of those icons on screen, but many more you actually use. So think about whenever you click that save button or the save icon, that's something that was designed by her. So the story goes that Keir was building a life-sized hog sculpture commissioned by a museum, and when she was welding that sculpture, she received a phone call from a high school friend named Andy Hertzfeld, and he wanted her to hand draw a few icons and font elements to inspire the upcoming Mac computer. And then she said, well, okay, if you can give me an Apple II computer, in exchange of that, I will do this. But she didn't have any experience in computer graphics and didn't know the first thing about designing typeface or pixel art or anything related to that. So she used her experiences of mosaics, needlepoint, and pointillism to create icon, and she mocked up several 32 by 32 pixel representations of software commands and applications which were going to be part of the Mac. And these includes the icon of scissors for the cut command, a finger for the paste, and a paintbrush for representing Mac Paint, which was kind of like the application of the time in 1983 when it was launched. So because of her art experience and the fact that she studied with somebody in high school who ended up working at Apple, she got involved in that particular process. But her imagination and creativity allowed operating systems to move beyond text and written commands and allow generations of people to start interacting with computers. And if you can think about that, all these magical interfaces that we now get wouldn't have been possible without the early work that she did. Now let's just go a bit back in history and back to that Battle of the North Atlantic, where processors were becoming powerful, data was being read slowly from tapes and disks, and you had IBM on one side in the US and you had Manchester University on the other side in the UK. So we're talking about the late 40s, early 50s, that kind of time period. And that was the time which was the birth of the ROM, and hardware instructions were now possible. You created read-only memory and you could load basic instructions in there, basic input-output systems. All of that was now possible at that point in time, and both sides of the Atlantic were trying to create computer systems which didn't require punch cards. And over time, this caused another problem, that the basic input-output systems, the basic instructions you could put in ROM weren't enough to operate a computer system. And there was a great need for an operating system, because once you loaded the basic input-output systems and you got the hardware working, you needed to play with applications, and more complex applications were being created, but you were going back to the same old approach of loading them the traditional way. So an operating system itself was needed to provide both the environment in which applications can be run and that usable interface between humans and computers. It often disguises that complexity of computer hardware. Computers are very complex: logic gates, various different instruction sets, binary, and anything that we can do to hide that complexity means that lots more people can end up using it. Now, this is very, very important, because often in an exam question, you're asked for the need for an operating system, so do take these notes down. And finally, the human-computer interface is usually achieved through a graphical user interface, commonly called GUI, although it is possible to use a command line interface, CLI, if the user directly wishes to communicate with the computer. However, most modern operating systems use GUI, and those graphical nature makes it very accessible for a lot of people. So let's start delving into user interfaces. So a CLI, or a command line interface, requires the user to type instructions, to choose options from menus, open software, and so on. So these are text commands which are normally typed at a prompt. And there are a lot of these commands, for example, to save, to load, to visualize what's in a directory or a folder. And the user therefore has to learn a number of commands which must be typed in exactly with no mistakes. So think of this as programming in Python or any other language, where if your syntax isn't correct, the command doesn't work. The advantage of CLI is that the user is in direct communication with the computer and is not restricted by a number of predetermined options. So you have greater control over the computer, the operating system, and that allows you to do a lot more complex things. So CLIs are normally used by experts or in specialist environments these days. They're still around, but most often than not, you'll probably see a graphical user interface. And if you wanted to see a CLI, you can look in your own operating system and there will be an option available for you to see a command prompt somewhere. I think Mac has terminal and Windows have command prompts, so you can have a look at those in your own time. Now, a graphical user interface allows the user to interact using pictures or symbols, which are normally called icons. And a whole sequence of CLI instructions can often be represented by a single icon. And GUIs or GUIs use various technologies and devices to provide the user interface. And one of the first commonly used GUI environments was known as Windows icons, menus, and pointing device. So look at your mouse, that's the pointing device. You'll have Windows icons and menus all available in most operating systems these days. And this was developed for the use on personal computers or PCs. A mouse is used to control a cursor, and icons are selected to open and run windows, and each window contains an application, hence the name Windows for Microsoft's operating system. Now, modern computer systems allow several windows to be open at the same time, which give you the impression of multitasking. A Windows manager looks after the interaction between the various windows, the applications, and the windowing system, which handles the pointing devices and the cursor's position. So when you move your cursor from one window to another, it knows that when you click, which application should register that click. However, smartphones, tablets, and many computers now use a post-WIMP interaction system where fingers are in contact with the screen, allowing actions such as pinching and rotating, which are difficult using a single pointer and a device such as a mouse. Also, simply tapping the icon with a finger or a stylus will often launch the application. And these types of user interfaces are known as post-WIMP interfaces, where multiple points of contact are used to interact with the computer. And of course, you've probably seen those videos where we're now looking at going beyond that. Our voice is part of that interface, and we're also looking at virtual reality and gestures which can be detected without touching anything. So all of that is part of human-computer interfaces and user interfaces. Now, all the UI or user interfaces allow us to do is to interact with the operating system or the computer basically. And we need to understand what the operating system actually does. So what do we interact with it for? Now, the operating system itself is a core group of technologies which are bunched together, and it has a lot of different tasks. Now, we already have the definition of an operating system given to you earlier. Now we're going to be looking at what kind of tasks that are possible in an operating system. So it allows you to manage the hardware, manage the files, the memory, security, and processes, and we'll define each of these in due course. These are the 5 key categories that we need to study. So we're going to be looking at memory management as our first one. Now, memory management can be broken down into 3 parts: memory optimization, memory organization, and memory protection. Optimization is used to determine how computer memory is allocated and deallocated when a number of applications are running simultaneously. It determines whether they're stored in memory at what locations. It must therefore keep a track of all allocated memory and free memory available for use by applications. To maintain optimization of memory, it will also swap data to and from the hard disk drive or the SSD. So think about it this way, that we've got this fixed amount of RAM, and these applications want to use that RAM. And if you gave the applications that control, they would like to be very resource hungry and they would like to consume all of the RAM. So the operating system optimizes the use of the memory to ensure that every application is given a fair chance of operation and running, and it manages the memory in the best way possible. It optimizes it. Memory organization, on the other hand, determines how much memory is allocated to an application and how the memory can be split up in the most appropriate or efficient manner. And this can be done with the use of a single, which is called contiguous allocation. So that keyword contiguous might come up in an exam, so make sure you know what it is. It's a single allocation where all the memory is made available to a single application. Then you've got partitioned allocation, where memory is split up into different contiguous or blocks, and memory management then allocates a partition to an application. So if you've got 2 or 3 running, then it'll divide it into blocks which are contiguous, which means they're next to each other, and it allocates it to each application that wants it. Then you've got page memory, which is similar to partition allocation, but each partition is of a fixed size. And this is used in virtual memory systems, and we'll look at that in a bit more detail later. And finally, you've got segmented memory, which is different because memory blocks are not contiguous. Each memory or each segment of memory will be a logical grouping of data, such as data which may make up an array, but they might not be next to each other. Okay, so that's segmented memory. Now, each of these 4 are critical for you to understand, so please make sure you write them down, jot them down, and you understand what they are. So memory organization in a single contiguous allocation, partitioned allocation, page memory, and segmented memory, what all of these are. If you do have any questions about these 4, do send a comment to me or catch up with me. Otherwise, I think that's all we want to talk about memory organization at this particular point in time. The next and the final part was memory protection. And memory protection ensures that 2 competing applications cannot use the same memory location at the same time. Without it, data could be lost, applications could produce incorrect results, there could be security issues, or the computer may crash itself. Memory protection and memory organization are different aspects, and operating system may use a typical type of memory organization. For example, it might use paging or segmentation, but it's always important that no two applications can occupy the same part of memory. Therefore, memory protection must always be a part of any type of memory organization used. So it's critical that operating systems have this facility built in. It doesn't matter whether you're using paging or segmentation, but memory protection is a must. Now on screen you see a nice little diagram that shows how this could work. There are addresses, then a boundary location, and then the next application, boundary location, and so forth. So you will have an upper limit and a boundary location limit. So do pause the video and study it. That kind of gives you an idea of how memory protection can be implemented, and especially how a fence can be built in, which defines the boundary between the operating system and the application. The next part is security management, and security management ensures the integrity, confidentiality, and availability of data. And this can be achieved by carrying out operating system updates as and when they become available, ensuring that antivirus software and other security software is always up to date, communicating with, for example, firewalls to check that all traffic to and from the computer is genuine, making use of privileges to prevent users entering private areas on a computer, which permits multi-user activity, for example, maintaining access rights for all users, read-only, write, all of those kind of things, offering the ability for recovery of data and system restore when it's been lost or corrupted, helping to prevent illegal intrusion to the computer system, also ensuring the privacy of data, so encryption might be part of that process as well. So security management covers a lot of security related areas. So nothing major here really. This is pretty straightforward. And we'll move on to the next part, which is process management. A process is defined as a program which is being run on a computer. And process management involves the allocation of resources and permits the sharing and exchange of data, thus allowing all processes or all programs to be fully synchronized. And this is achieved by scheduling of resources, resolution of software conflicts, interrupts, use of queues, and so on. That's all you need to know about process management at this particular point in time when you talk about it in the context of an operating system, that a process is a program, and process management involves the allocation of resources and permits the sharing and exchange of data, making sure that all the processes are fully synchronized. Hardware management is the next part of an operating system's tasks, and it involves all input and output peripheral devices. So the functions of hardware management include communicating with all input and output devices using device drivers, translating data from a file into a format that the input-output device can understand, again using device drivers, ensuring each hardware resource has a priority so that it can be used and released as required. Now, the management of input-output devices is essentially the control and management of queues and buffers. For example, when printing out a document, the printer management locates and loads the printer driver into memory. It sends data to the printer buffer ready for printing, sends data to a printer queue if the printer is busy or the print job has a low priority before sending everything to the printer buffer. It sends various control commands to the printer throughout the printing process, and it receives and handles error messages and interrupts from the printer. Now, the most common type of hardware that we normally talk about in exams is the printer. However, there are lots of other devices out there as well, so you might want to have a look at those as well. Hardware management is pretty straightforward. The key element is understanding that an operating system won't be able to talk to a hardware device without the use of a device driver. And a device driver is a piece of software which is normally coded by the manufacturer of that particular device, and it allows communication to occur between the operating system and that particular hardware device. The main tasks of file management include defining the file naming conventions which can be used. For example, docx, where the extension can be other ones like .bat, .htm, .dbf, .txt, and so on. It allows performing specific tasks such as creating, opening, closing, deleting, renaming, copying, moving files. It maintains the directory structures, ensures access control mechanisms are maintained, such as access rights to files, password protection, making files available for editing, locking files, and so on. So a lot of file-related work is permitted under file management. Again, things like storage formats like an FAT or NTFS if Windows is being used, a Mac OS journal format is used for Mac OSs, depending on which type of disk formatter is used. And finally, ensuring memory allocations for a file by reading it from a hard disk drive or SSD and loading it into memory. All of this is part of file management. Now, that's all you need to know about the various different tasks that are part of an operating system. And hopefully you've jotted those down and you can define those. Utility software is also part of an operating system, and these are basic utility programs which are built in. However, users might be able to install their own ones if needs be. And a typical example is a virus checker, which users often install their own ones instead of using the ones built into the operating system. The software is usually initiated by the user, but some, such as virus checkers, can be set up to constantly run in the background as well. And utility software offered by most operating systems include hard disk formatters, virus checkers, defragmentation software, disk content analysis or repair software, file compression, backup software, firewalls, and so forth. Now, the ones that you see on screen, you need to know all of these and their operation quite clearly because these are written about in the syllabus. And chances are that you will know quite a lot of these from experience already. So your task is to perhaps pick the ones that you don't know about and maybe get some information about them through active research. Do report back to me, so perhaps create a document with each of these and jot a few lines down about what they are. Now we're going to be looking at program libraries next. Program libraries are used when software is under development and the programmer can utilize pre-written subroutines in their own programs. Think about random, math, all of those libraries that are used in Python. They save considerable development time because you don't have to code them yourself. And they help software developers who wish to use dynamic linked libraries, subroutines in their own programs. So these subroutines must be available at runtime and they should be part of the operating system as well. So when these software routines are written, such as like sort routines, they are frequently saved in a program library for future use by other programmers. A program stored in a program library is known as a library program. We also have the term library routines to describe subroutines which could be used in another piece of software under development. So there are two different things. One is a standalone program, the other one is just a software routine or a library routine which can be part of another program. Now, developing software using program libraries removes the need to rewrite the many routines every single time. So it saves time and cost because programmers and development time costs money. It leads to modular programming, which means several programmers can be working on the same piece of software at the same time. It allows continuity with other games or other software that may be part of a whole range. For example, in education, there may be a whole suite of programs available. Allows the maintenance of a corporate image in all the software being developed by a particular company. And it saves considerable development time having to test each routine since the routines are fully tested in other software and should be error-free. So it saves that time and it ensures that your programs are bug-free or error-free. So quite a lot of advantages in using program libraries. Now, all operating systems have two program libraries containing library programs and library routines. These are static and dynamic. So in static libraries, software being developed is linked to executable code in the library at the time of compilation. So the library routines would be embedded directly into the new program code. In dynamic libraries, software being developed is not linked to the library routines until actual runtime. These are known as dynamic linked library files or DLL files. And these library routines would be standalone files only being accessed as required by the new program. The routines will be available to several applications at the same time. When using DLL, since the library routines are not loaded into RAM until required, memory is often saved and software runs a lot faster. For example, suppose we are writing new software which allows access to a printer as part of the specification. The main program will be developed and compiled. Once the object code is run, it will only access and load up the printer routine from DLL or the dynamic linked libraries when required by the user of the program. The main program will only contain a link to the printer library routine and will not contain any of the actual code that's involved. So think about it this way. When you're coding a program, using a static library means you will use the library routine or the code in your actual program, and it will be compiled and saved with it. Whereas with a dynamic library, you are just passing the reference address to that code, and that code will not be loaded unless it is asked so by the user. So sometimes you might not even need to load it up. That means your program is actually going to be smaller and require less resources. Now on screen, you can see some benefits and disadvantages of using DLL files. So do pause the video and get these down. The executable code of the main program is much smaller since the DLL files are only loaded into the memory at runtime. It's possible to make changes to DLL files independently, so you can update them as necessary. DLL files can be made available to a number of applications at the same time, and they save memory and also execution time. The disadvantage is that the executable code is not self-contained. Therefore, if the DLL files are not installed on someone's operating system, it could lead to crashes. And any DLL linking software in the main program needs to be available at runtime to make those links work. So there is some kind of loading mechanism there that needs to be part of your main program. If any of the DLL files have been changed, this could also lead to the main program giving unexpected results or crashing. For example, you might have coded on version 1 of the DLL file and version 2 is released, and that could cause an issue. And of course, malicious changes to DLL files could be due to the result of malware as well, which can open the door to all sorts of issues and viruses and crashes that perhaps you can avoid if you had the code in your own application in the first place. Now that's all for today. Hopefully you should be able to define the purpose of an operating system. You should be able to list the main tasks of an operating system and perhaps define them in greater depth. You should understand what utility software is, what program libraries are, what is meant by dynamic link library files, and explain the benefits and disadvantages of DLLs. Please do make sure that you are aware of the different types of utility software. So do that activity, because that will give you a greater understanding of the different examples of utility software. Chances are that you already know certain types like firewalls and virus checkers from previous years, but it's also useful to find out a lot about disk repair software and disk defragmentation software if you're not familiar with that. So that's all for today. If you do have any questions, as usual, get back to me, and I will see you in the next one.